digital design implementation. Handled most of our analog implementations, and I was in charge of overall design implementation and requirements. Now, our design mostly is generally focused around active electronic control for active LED coolers. Now, why do you need active LED coolers? Our specific market is for the LED light bulb market. LED light bulbs suffer currently from cost issues as they reduce. Those, however, are coming down through high volume manufacturing, and they also suffer from lifespan issues due to the fact that LED light bulbs are incredibly hot when they run. Now, if you can lower the operating temperature of an LED by even a few degrees Celsius, you can greatly expand its lifespan, thereby increase its cost effectiveness. So specifically, this is where Nuventix comes in. They produce the SynJet motor. Synthetic jet uses synthetic pulses of air to shoot across the heatsink. It vibrates like a speaker, and it's a lot easier if I can just show you in a demo, which we have set up at our booth. Now, they contract with Texas Instruments, who's in charge of this project, to produce their active electronics that actually control the device, and we were brought in to basically produce an alternative. Their current solution is the C1000 series of controllers. It is sophisticated and it's high precision, plus or minus 1% tolerance around its resonant frequency of the motor, but it's expensive. And in a high volume application like the LED light bulb market, cents saved on an IC translates to costs much farther than the line of manufacturing costs. So we were brought in to mostly focus on low cost. Now, to give you a breakdown of our design, it hinges around a series of D flip-flops cascaded together to get a ripple step function, the frequency of which is set by a pocket timer network. We send that through a second order passive LPF, which clips off those hard edges, resolve a smooth sine wave. We separate that visual stage with the buffer and send it to a differential drive stage, which is centered around 6 volts DC and is capable of driving all the way up to 8 volts peak to peak at 1 watt power to as low as you'd like it, depending on the motor application. Now, where that comes in is why is this an advantageous design? First, our number one low-cost goal is met. Early estimates from TI are looking at probably a 50% reduction in cost compared to their C1000 solution. It provides very easily modularity for Nuventix. Basically, if they want to pair this with a motor, the only thing they need to change out is a resistor to set the open loop gain, and they change out another capacitor to set the frequency around the resonant frequency of the motor in question. So it's very easy from a manufacturing standpoint design to compare with their various lines of motors. The one I passed around is just one of many motors with different resonant frequencies and power requirements. And finally, it's our feature design expansions. We would like to implement resonance tracking using a closed loop. That single resistor that sets the gain, our idea is to use a variable resistance potentiometer, basically. It would take an input voltage of the back EMF in the motor using a sense coil in the motor to sense the displacement of the motor and vary the input gain to the system. And that's something that if Nuventix likes our idea at our presentation to them next week, they will take up and look at doing. They would have to produce a specific specialized motor with a sense coil to do that. And finally, we'd like to test this in an IC prototype that we have right now as a breadboard prototype per instructions by TI before they take it the next step to IC. And as such, it's limited. We can only fit 60 flip-flops on our board, which means you have a certain amount of quantization or you just plain can't avoid. So with that, we do have work done. We invite all of you guys to come check it out. Are there any questions?
How much does it cost?
I can't say that because of NDA restrictions, I'm afraid.
Specifically
told them
replacing. Well, less. No. You said the application is increase the lifespan of LED bulbs. How much does it cost compared to replacement bulbs?
You're talking about the LED? I'm not sure that I understand your question because this is what Nuventix does. Is they don't actually manufacture like the light bulb. Right. They manufacture the heatsink and then the produce.
But you said the purpose is to increase the lifespan of a device such as a bulb. Correct? Right. So is this motor going to be cost prohibitive? Whereas would I want a motor that makes it last longer, or is it so expensive that it's just cheaper to replace the broken part?
I honestly can't speak to that. It must have a market because Nuventix has been successful so far. We were concerned that, again, this is a project contracted through TI for Nuventix. I don't have as much visibility that I don't want to speak to you and give you bad information on that. I just don't know as much about Nuventix's business model as I do about TI's stake in this project.
What's TI's feedback to you being on the project?
We actually just met with them this past week. It's been positive, and we have another presentation where we're going to go formal write-up and a representative from Nuventix stage where we have a working demo of the motor. They're just ready. If Ventix likes it because they're the customers, then TI will take it and run with it along past when we'll get involved in the project.
Any more questions?
How many prototypes did it take you to get to this point?
The thing is that because we came up with a custom solution, we went through many iterations. And initially, we attempted. The nice thing is that we ended up coming with many design documents at the end that they could actually go back and look at. For example, what's on our poster right now is a solution that uses a positive and a negative 12-volt rail. What we end up designing at the end is something that you basically only need 12 volts input into it, and it runs. It's ready to go straight out into an LED light bulb scenario, ready to go. So I would say probably actual prototypes and